Hi everyone, I'm presenting our work HRTF Field Unifying Measured HRTF Magnitude Representation with Neural Fields. HRTF stands for Head-Related Transfer Function. It describes how an ear receives sound from a sound source. To be more specific, mathematically it describes spatial filtering effects introduced by our torso, head, and ear shape. It also differs from person to person due to geometry differences. So we are interested in getting personalized HRTFs. The measurement of HRTF is not easy. We usually need microphones inserted in the listener's ears, and we should have multiple loudspeakers arranged around an arc and rotate in the horizontal direction. And recording requires an anechoic room, and it's very time-consuming to record one person's HRTF. So if we can use data-driven methods to predict personalized HRTF, that would be great. We can use some machine learning models to predict some representation of HRTF, then retrieve HRTF at a given location from this representation. But there are problems using data-driven method with the existing databases. First, each database only contains small numbers of subjects, but HRTF is a very high-dimensional data. For each spatial location and for each ear, it is a function of frequency. So if we want to represent one person's HRTF, it's the number of spatial locations times the number of ears times the number of frequency beams. But the existing databases only contain dozens of subjects, shown in the bottom right table. The maximum number of subjects in one database is only about 100. And more importantly, the spatial sampling schemes across databases are different. This will cause discrepancy in spatial resolution. From the left figure, I listed 10 existing databases that are publicly available, and we can see that their spatial sampling schemes are very different. And on the right figure, we show that the HRTF on the mid-sagittal plane have the spatial resolution differences from two different databases. So in our work, we propose to represent HRTFs of a single subject with a neural field. By definition, HRTF of 1 year of a subject is a functional defined on the continuous sphere. It is a function that can be calculated from the sound pressure at the location divided by the reference sound pressure. And it is a function in terms of the azimuth angle theta and elevation angle phi. We propose to represent this continuous function with a neural field, a deep neural network to parameterize the function. And the architecture we use is the sinusoidal representation network, which is a multi-layer perceptron, but use sine as the activation function. The input of the siren network is the theta and phi, and the output is the magnitude across different frequencies. So this is for representing HRTF of a single subject, but we're interested in personalized HRTF. So how do we represent HRTF across different subjects? We introduce a latent vector Z to represent each person's identity, and we want to use a generative model that can learn a mapping from the sound direction and this latent code to a subject's HRTF. So the Z is in the dimension of D. So the mapping we learn is from the dimension of 2 plus D to K. K is the number of frequency beams. And the generative model we use here is the implicit gradient origin network. And the training pipeline can be shown as follows, where the latent code and the network are jointly learned. And we did 3 experiments to verify the effectiveness of our method. First, we work on interpolation with the learned HRTF field. We perform HRTF interpolation on the REC grids by holding out half of the locations as the desired locations, and the other half are the observed positions. We use three settings to compare with the mathematical baselines VBAP and bilinear method. We can show that ours T and ours E are having similar results with the bilinear method. This shows that our method are effective to perform HRTF interpolation. And the more exciting experiment is we do the conditional generation from randomly observed locations. So for this experiment, we have much fewer and irregular observed locations. And we first infer a latent code Z from the observed locations, and then use the generative model to generate all the other locations HRTFs. So in this scenario, the bilinear method will not work. And from the results, our method have better performance than the VBAP method, and is also more robust across different subjects in terms of the standard deviation. The last experiments we did is the generation by sampling from the latent space. In the figure we show here, the leftmost and the rightmost are two subjects HRTFs drawn from the dataset. And we first infer their latent code Z1 and Z2, and we perform interpolation on the latent space. And we have ZT here, with T as the different ratios between these two latent codes. And from ZT, we use our generative model to generate HRTFs. From the figure, we can see that the generated HRTF samples follow the HRTF magnitudes, and the transition of the synthesized HRTFs from left to right is very smooth. That shows that we successfully models the HRTF with this generative model. So the conclusions here are neural fields is effective in representing HRTFs, and it is agnostic to the specific spatial sampling schemes adopted by different HRTF datasets. We propose a generative model that learns the manifold information for the neural field representation and can perform well in interpolation and generation tasks. We believe that the proposed HRTF field will significantly advance the data-driven research on HRTF personalization. Thank you for your attention. If you have any questions, feel free to reach out to me.